Hello everyone, my name is Michael Horn. Today I will be completing a process dynamics and control homework problem homework 4, problem set part C. And before we begin, I want to read everyone the problem statement so we are all on the same page. So, first we will draw and explain the block diagram for a Smith predictor controlled system with dead time. And then we will second derive that closed loop response of a Smith predictor controlled system to changes in set point and disturbance. And then finally, we are going to open up Google Colab as we normally do at the end, and we're going to simulate that closed loop response of a first order system with the gain of 1, time constant 2. Whole bunch of specifications that I'll explain, more once we get into Colab. And then we're going to compare that with the response of a closed loop system without dead time compensation. And finally, for both cases, we're going to use a PI controller with controller gain and reset the time of 5 and 10 respectively. So as you can see, we're going to be working on the iPad here. And then first thing is we're going to draw and explain this block diagram. So let's begin. So let's first begin with 3 blocks. So first here, we are going to draw this block. Let's actually use a smaller size. So we're going to draw a block here. And this is going to be our process. So we're going to GP process. We're going to draw a horizontal line connecting it to another box here. Oh, I want these to be the same size. So let's do this. Darn it. I'm messing it up. So, all right, we're just going to draw this again here. And this is going to be the controller. So we have GC, controller. These will be connected here by a horizontal line. And then here, we're going to have an equation assigned to this process box, and that is going to be KE to the power of theta S over tau S plus 1. And again, these are derived from the equations that we did in previous videos. And then we are going to have a straight line going down to another box. And this box is going to be G bar P of the process, and this formula is going to be K bar over tau bar S plus 1. So I have actually slid this down because we're going to need some extra room. So what's going to come from this GP is that I'm going to move this down so we can draw our correct line. This goes here, and we are going to also have a line here, and this line is going to go into another box, and this box is going to have E theta S, and coming out of this box we're actually going to go into exchanger. And then from here, this is going to have another output going straight up, and it is going to go into the same type of plus minus, and then this will be recycled back into the controller. And then from here we have this, and again we are solving for y here. So we have our YSP here, and then coming up top we have another box. This is the disturbance. We go back to our blank to show the flow of this, and this will be GD. So now I actually wrote this incorrectly, this part. This is just Y. And so there's going to actually be another entire loop here, so you're going to add another controller going in here, and this controller is going to be connected to this other controller on the right, and here is YSP going in and coming out as Y. So this is the complete diagram. Actually, let me write here, simulated model. Okay, there we go. So this is the complete diagram that we are going to solve. So now the second part of this is going to be actually deriving an equation. And so to do this, we're actually going to redraw a lot of this. So again, we have this square here, which we will label as GC. And then down here, we're going to have another. And we're actually going to make this one bigger just so I can write more in it. This is going to be GP parentheses 1 minus e to the negative theta s. And these will not be connected. And then this GC box will be going into a GP box. So connect those with an arrow. This will go down and through with an arrow going this way and back up. And then in here, actually, I'm going to do this. We have a controller here that is being, YSP is being put into it. And then over here we have another controller going out to Y. And then up here we have our disturbance GD. And the main portion that we will be looking at are these two boxes in this system. So now let us begin with the actual algebra of this problem. So the first equation that we have is y, which we are solving for. And y is going to be equal, zoom in a little bit, y is going to be equal to gp times gc divided by r1 plus gc g bar p times 1 minus e to the negative theta s. And then all of this will be multiplied by YSP. And we're actually going to rewrite this as a variable as alpha. So then this becomes y equals d times gd plus alpha times y minus y set point. Now again, you rearrange this even more, you get y minus alpha equals just d times gd plus alpha YSP. And then you arrive at the final equation after you substitute in, and you get y equals d times gd over 1 minus alpha plus alpha over 1 minus alpha times YSP. And so this is the final derived equation that we have been looking for. And now we're going to be able to go into Colab and use this equation to run our simulations. So let's begin coding. I have Colab here, and as you can see, I've already imported the libraries. And so the first part that we are going to do is actually input all of our specifications from the problem statement. KC is going to be equal to 5, tau initial is going to be equal to 10, GC is going to be equal to KC times 1 plus 1 divided by that tau initial, but it's going to be multiplied by S. K is going to be 1. Tau is going to be equal to 2. And theta is going to be equal to 10.5. Now let's go to the next set of variables, which is going to be K tilde. That is going to be equal to 0.95. We have tau tilde. That's going to be equal to 2.2. And then we have theta tilde, which is going to be equal to 10. Now we need to put in some of our equations. So our first is GP, and GP is going to be equal to K to the power of negative theta S divided by tau times S plus 1. Then we also need our GP tilde, which is going to be equal to K underscore tilde divided by tau tilde times S plus 1. And then we have T and Y, and those are going to be equal to sim of GC times GP divided by 1 plus GC times GP, all of that, and then we do lambda of t at 1 n is equal to 1,000, and dt is going to equal to 0.1. So let's run this, make sure everything's okay. Oop. This is supposed to become invalid syntax. Oh, it's supposed to be a comma. 1 second, let me fix this. All right, that was a quick fix. I had two little parentheses here, so it was kind of bugging out. But so now we're gonna actually make our subplots. Make subplots fig dot add scatter. We want our x axis to be equal to time. Y is just gonna equal our y variable. And then we want mode to be equal to lines. And finally, we want to update the actual dimensions. Fig dot update underscore layout. We want the width to be equal to 600. Height to be equal to 400. So let's run this and see what we get. I will unpause once it has come up. So we have completed this section. It just took a little while to run. But anyway, as you can see, it is a very stable horizontal line until the dead time runs out. And once that dead time runs out, you see these larger oscillations in the line. And so now we're going to make some adjustments to these specifications and just play around to see what happens next. So now the next goal of this is to actually see what happens to this process when, oh my gosh, this keeps bugging out, when there is no dead time. So this one has dead time, and let's see what happens now when there is not. And so the first thing that we're going to want to do is our alpha value, which we will label as A, and that is going to be equal to GC times GP. This is going to be all divided by 1 plus GC. And again, we're getting all these variables from the equations we derived earlier. 1 minus exp of negative theta underscore tilde times s. And then we have t y underscore servo. That is going to be equal to sim of our alpha value divided by 1 plus alpha, comma, lambda t. And in here we're going to have n equal 1,000. And the derivative of time is going to be equal to 0.1. We want GD to be equal to GP. And then we want our and we want ty underscore disturb to be equal to sim GD divided by 1 plus our alpha variable. In here we want lambda t, t divided by 10, sorry, t less than 10. We were able to close that off. And now we need to, make some plots. So we're going to copy this as a template just because it saves us some time. So here, this top line, fine, scatter, except this time we want x to equal t. We want y to equal y underscore servo. Mode is going to be lines, and we want to name this one servo. And then we need another one of these. So we will put that there. But this time we want this to be equal to disturb. We want modes to lines, but then we want disturb reject. And same there. So let's run this and see what we get. Invalid syntax. I'll be right back after I fix this. Alright, we are back. It was just a simple parenthesis error again. So you can see as the dead time, you can see the server starts to kind of react, I would say, once you see a disturbance rejection. So this huge oscillation in the red line shows a very big spike in the blue line. And then as the variance in the red line diminishes, you see the oscillations or heartbeat in that servo line get smaller and smaller and smaller. So this has been a summary of homework 4 part C. I hope everyone is able to follow along, and thank you for watching.